Hi everyone, welcome to this video series on feature engineering techniques. We are discussing feature selection category of algorithms, focusing on embedded methods. The key point about the embedded methods is that these techniques are integrated seamlessly with the machine learning training processes. In the previous video, we talked about the intuition behind the embedding or regularization. Let's get started with the technical implementation. Just a quick view on the taxonomy of the feature engineering methods. Right now, we are discussing embedded methods, and we have discussed the intuition behind the embedding, and I'm going to show you the implementation of some of the embedded or embedding techniques or regularization techniques called Lasso, Ridge, and Elastic Net. We will not be covering the tree-based regularization. Probably in some other video, I'll cover machine learning-based regularization. Okay, so let's talk about the technical aspects of L1 and L2 regularization. We will be covering the concepts and also we will be covering the implementation side of it. And at the end, I'm going to show you the Python code demos. So where regularization actually fits into the ML story is like this. For example, you have the models, trained with polynomial of degree 2 and degree 10 and 20. And you have training error and testing error, these two measures. Since this one is kind of generalized model, so the error is acceptable, both training and testing error. But this one is overfitted, and the training error is low in this case, whereas the testing error would be high because it is overfitted model, and this is severely overfitted. So probably the training error is very, very small, like 0, and the testing error is highly varying or very high. So what regularization actually does is picks up the overfitted model, regularize the overfitted model, and give us a sort of generalized model. This is how regularization fits into the machine learning orchestration. Let's take an example. So these are my training samples, the blue dots, and let's say the red one is actually the model. So the blue dot represents the training sample, and the red line is your regression line, and it would have some intercept. In this plot, there is no intercept, but normally it will be there. And the 0 training error because the model is going through the blue dot or the training samples, so there are no training errors, and hence this model is overfitted model. Now with this overfitted model, which is the red line here, and the blue dots are your training points, let's have some testing points, and these green ones are your testing points. Now notice with this situation, you have 0 training error and high testing error. And we would like to rectify this situation. So if we can change the model from the red line to alternate blue line by using regularization. This blue line is being shown as adjusted regression line, essentially is a regularized model. So red dashed line represents the original regression line that I showed you in the previous slide, and the blue dashed line represents the regularized model. How situations change with this, let's take a look at it. So initially, with the baseline model, you have 0 training error and a high testing error. With the regularized model, you are compromising with some training error, but at the same time, the testing error is somewhat decreased. This is what the regularization enables us with. So essentially, the training error increases with the regularization, but the testing error decreases. And thereby, it enables generalization. So shifting of the regression line is called regularization. Let's do a quick recap how regularization will be applied to, let's say, linear regression. So let's do a quick recap of how linear regression model is implemented. So this is how you have a equation of a linear regression, x1, x2, and xn, and hypothesis function, which is basically your prediction. And the loss function is the error in the prediction. So this is your prediction. This is the actual value, and the square it. So it's going to give you mean square error. Sum them up and normalize by dividing by the number of samples. So this is your loss function in a traditional linear regression. Now the objective function, or which is basically the function used by the gradient descent to minimize the loss function in order to find the optimal value of the parameters or the coefficients. And for example, the basic linear regression uses a closed form solution, which is this function here, or this formula gives you the closed form solution, which is a data set. So this is a data set, transpose data set, inverse, and data set again transpose with the response variable. This is going to return you all the coefficients here, theta 1, theta 2, theta 3, theta n. So we need to do something with this basic linear regression model in order to achieve regularization. So this is how a typical linear regression works. Now, essentially, what we need to do is to add something to the loss function in a basic linear regression. And with the overfitted model, you have low training error, and that means the model is quite flexible, and it knows only the training set. But with the testing set, it will give you lots of a high variance in the error. And hence, we have a generalization concern. In order to fix this, we add a penalty term to the loss function in linear regression. So regularization will add a penalty term to the loss function. Let's take a look at it, how this addition of a loss function really helps in achieving a generalized solution. So how is the L1, which is also called Lasso regularization, and how this penalty term is expressed? So the penalty term for L1 regularization is simply the sum of absolute values, which is this. So let me expand what this actually means. Is, let's say you have two variables, W1 and W2 are the coefficients. So W1 x1, W2 x2. So this one simply means that take the absolute and take the absolute here and add them together. This is the penalty term. And we are going to multiply with some alpha, which is a configurable parameter. We'll see what is the significance of this alpha. So this equation simply means configure the penalty term to the loss function. So I marked alpha here in a box because I need to explain it, what this alpha is all about. How does it actually help in regularization? And Wj is simply the individual coefficients of the model, like W1, W2, and n is the number of features or number of columns in the model. Now, I've also boxed this particular sentence, the L1 penalty encourages sparsity in the model. This also needs explanation, which I'm going to do in the subsequent slide. Essentially, because of this penalty term, the coefficients which are overfitted without the regularization will get optimized, or it might get closer to zero. Now, these 2 points need further clarification or elaboration, which we will do in the next slide. Since some of the coefficients are turning zero, this is also used as feature selection. So the columns or the features for which the coefficients turn zero, those are useless column for the model. So we can remove those columns from the data set. So L1 regularization also plays as an alternative in feature selection or feature engineering. Now, since the coefficients are turning zero, some of the coefficients, not all, some of the coefficients are turning zero, it will lead to a sparse model. Now, let me explain what this actually means. Let's say you have W1, W2, W3, and W4, and let's say W500. So many variables. Out of this one, and let's say W77, these are turning to zero because of regularization. Now, because of the zero value in the coefficients vector, this is turning into a sparse vector representation. Now, this is useful, but I marked it red, but this is useful in some way, which is feature selection. We will understand how those are, how for some of the coefficients, it will become zero because of L1 regularization. Now let's understand the penalty term for L2 regularization. This is also called ridge regularization. Quite similar, but some of the squared value. That means, let me explain here also. Previously, we had some of the absolute value. Here, we have some of the squared value. That means, let's say you have two variables, so two coefficients, and W1 square and W2 square, and that's your penalty term. And we're going to multiply with the alpha, like in the previous case, like in a L1 regularization. Here also, we're going to multiply with alpha. We're going to see what's the use of alpha as a configurable parameter pretty soon. Wj is the coefficients, n is the number of features. L2 penalty discourages overly large values, which is similar to L1 regularization. But the difference here is L2 does not result in any of the coefficients turning to zero. So some of the coefficients will turn very, very close to zero, but not exactly zero. So L2 regularization cannot be used as feature engineering technique or feature selection technique. So what does it mean? That you have, let's say, W1, W2 up to W500. This will not give you a sparse model, but this will give you a dense representation. Every coefficient will have some value. None of them will be zero. Okay, so this is a dense representation. This is the difference between the L1 regularization and L2 regularization. Like in the previous case, I have also put a box here. We will discuss what is the significance of alpha in this L2 regularization as well. I've also boxed it, this particular phrase, L2 does not usually result in zero coefficient. We will understand why and how. Now, there is a slightly, a smart bit of regularization where we're going to combine L1 and L2 penalties together, and that's called elastic net. So simply combination of the L1 and L2 will give you a combined regularization effect. and also called elastic net. And again, alpha is used as a configuration parameter. We'll see what is the significance of alpha. And lambda is an additional parameter, which is basically a L1 ratio. So it's simply saying how much of L1 and how much of L2 that we need to add. So if lambda is 40%, then this particular regularization will be 40%, 0.4. This will be 0.6. So again, these are configurable parameter. So while tuning or while implementing, we need to find out the optimal value for lambda as well. And if lambda is 1, that means it's pure L1 regularization. If lambda is 0, that means it's pure L2 regularization. Adjusting lambda will give you a mechanism whereby we can have both L1 and L2 applied. But what is L1? Let's try to understand what is L1 here. What does it mean? So if you remember the formula that we talked about a while back, L1 is your weights matrix and the absolute value, right? So what it means is you have W1 absolute and W2 absolute. And if you constrain it to say some value, let's say 1, so whatever value of W1 and W2, it will always be 1. If that's the case, then you're going to get the shape of a diamond, which with the origin here, and this axis, let's say, is W1, and this axis is W2. So for different values of W1 and W2, if the constraint is put to 1, then it will always give you this particular shape. So L1 norm is always a diamond shape. So simply is defined as a sum of the absolute value, which is what we just discussed now here. These are the coefficients, let's say x1, x2, and xn. Take the absolute, add them together. That gives you the L1 penalty or L1 norm. So what's the intuition behind the L1 norm? Let's understand this. This is crucial. If we get this right, then we understand why some of the coefficients are turning 0 in case of L1, not in case of L2, and so on and so forth. One other good thing about the L1 regularization is the L1 norm, since we are taking only the absolute value, it is less sensitive to outlier compared to the L2 norm. So what does this alpha and lambda do in this formula that we have seen? So I showed you earlier. Let me write it here. So essentially the penalty is equal to alpha times the Wj here, sum of the Wj here. So this alpha, what does it do? So for various alpha, let's say, we can change the value from 0.1, 3, and 1, and 5, and 7 in the increasing order. Then you notice here the strength of the penalty term is increasing. That means higher the value of the lambda or alpha. So this is basically the same thing here. This will result in strong penalty. And this, because of the strong penalty, this will tend to shrink the coefficient. Now, this is another part that we need to understand why it is going to shrink. Just the opposite will happen if you have a lower value of lambda, then it will reduce the penalty. And then in that case, the diamond will be bigger. Now, this changing of the alpha value is what is very crucial in regularization. That means we need to find the optimal value for this alpha or lambda so that you have an optimal performance. Performance simply means the accuracy or mean square error or R2. Now, what about L2 norm then? L2 norm is again the Euclidean norm, which is basically square of the coefficients. So simply it is expressed like, square of the coefficient, then you take a square root, and it is similar to Euclidean norm. Let's say you have beta 1, beta 2, beta n, and then square each of the term, sum them up, and then take the square root, and that's going to give you L2 norm. Now this is the equation of a circle. So the L2 norm is a shape of a circle. Now this shape is intuition about this shape is important to understand the effect of regularization, which I'm going to show you in the next slide. So what we're going to do is, in the case of L1 regularization, this is your original mean square error, and we are adding the penalty term, which is the Manhattan or taxi cab, the absolute value of the coefficients. In case of L2, original mean square error and the Euclidean form of the norm. And this is your lambda or alpha that we need to optimize or find the optimal value during the training process. So what's the impact of regularization here? The regularization term after taking the derivative will be like this, essentially in case of your L2 regularization. After taking the derivative, this will take a shape of 2 times lambda and then the beta coefficient. Now this term being added in the objective function, this does the trick. What is this trick? It acts as a pull on each of the coefficient, and that discourages the coefficients to become too large. Why is it becoming too large? Because of in case of without regularization, your training process will fit the data, fit the coefficients to the training data, and since we have a overfitting case, the coefficients will become large anyway. We are adding regularization term to the objective function to reduce or shrink the coefficient. And because we are adding the penalty, that acts as a pull. Let's understand how this pull actually takes into effect. But how this pull really happens? So let's understand it. So when we have this lambda higher value, then this one also becomes large. Now the training process, where you have the objective function and then you have a function to minimize. Now in case of regularization, you have to minimize two things. One is the mean square error and the other one is penalty term. These two things we have to take into consideration. In fact, they are added. And as the lambda increases, what happens with the large value of lambda? The optimization algorithm will have a high penalty, and your usual mean square error will remain the same. Now, as part of optimization, the algorithm will try to find the balance between the penalty term and the mean squared error. So these two things will happen like a tug of war or trade-off. So the ridge regression tries to strike a balance between the training data and also the penalty term. I think it needs further more explanation. Let's take a look at let's take a look at a plot. Let's say this is a gradient descent, and without the penalty, you have the mean square error. With regularization, we have added one more term here. So this is your mean squared error, and this side is your penalty term. And this penalty term becomes larger or smaller based on this lambda. Now this does the trick. And how? Let's see here. Essentially, what happens is because of the penalty term that pushes the gradient towards zero. So this is your minimum point. And in this case, anyway, your gradient will be whatever the gradient that you have computed, and that gradient will be pulled towards zero. In the absence of regularization term, the optimization process will fit the coefficients based on the training data or training error or mean squared error. Now, after adding the term, the model will not use all the training data and find the optimal values of the coefficient. Rather, it will push the gradient towards zero a little faster. So your theta, suppose without the regularization, it was, let's say, 0.0, 3, something like this. Now, because it is pushing it faster, so your convergence is also faster. Now, with the penalty term added, this theta, a particular theta, let's say, theta 7, this theta 7 would be slightly different than 0.03, and this was causing overfitting, and this would be slightly like, 0.001 or something like that. So, uh, so with the regularization term, what is happening is the trade-off between the training error and the penalty term. Since we added the penalty term, the training error is not going all the way down to the last, minimum point. Rather, it converges rather fast, and hence the coefficients are slightly different than the coefficient that you would get when no penalty term or without regularization. Now, because of this, the effect that we get with the regularization is the shrinking of the coefficients. I hope this explanation makes sense. Now, the same thing will happen with L1 regularization or L2 regularization. The result of adding the penalty term is, for example, in case of ridge regression, because of the trade-off, is discourages the model from fitting the model to the training data very closely. So we are now taking the model a little bit away from the noises in the data or irrelevant features or redundant features in the training data because of the penalty term. And hence, it prevents the model to become too complex. Now, because of this control over the coefficients, we have a better generalization of the model. Now, another intuition is here, let's say, your mean square error, and without the penalty term, and since this is the minimum point, so this would be the coefficients. For example, so let's say this is theta 1 and theta 2. Now, when you add penalty term, which is basically your alpha and let's say wj absolute, and then the mean squared error, and then we take this and we take a minimum. When we take a derivative of this with respect to theta, then we have to minimize this. When you minimize, then what happens is then it takes these two functions mathematically, and the point of contact of this diamond, which is basically your L1 norm, and this is your mean squared error, which is a normal training function or loss function. So in this case, when you apply the penalty term, then the minimum may happen at the point of contact of these two functions. Now, let's say the point of contact is here. So your new theta 1 and new theta 2 is now shrunk. So this is how the optimization to the coefficients is happening because of the penalty term. Now, if you look at very closely again, because of the shape of the diamond, the point of contact could be at the very axis also. If that particular axis, or let's say the coefficient theta 2 is not influential to the model, then this could be that the point of contact would be right at the axis. Then in that case, the theta 2 will become 0. And this is how L1 gets us to a sparse, theta vector. And in a way, it helps us with the feature selection. In contrast, now L2 regularization, if you look at it here, so this is my L2 regularization. Here also the same thing. So you have the penalty term added. Just a second. Yeah, so penalty term added, and the point of contact would be just 1 second. Yeah, so the point of contact would be at any of these points here. All right. So, but if you look at it geometrically, the point of contact can never be the axis itself. So none of the coefficients will turn to 0. All the coefficients will be shrunk. Some of the coefficients might be very, very close to 0, but not 0. And hence, L2 regularization will always give you a dense representation of the theta or weights or coefficients. So summary is the L1 shrinkage is sparser because of the L1 diamond shape. Some of the coefficients can turn to 0. L2, on the other hand, is dense representation, and it will shrink all the coefficients towards 0 maybe, but not exactly 0. The choice of L1 and L2 will depend on the specific need of your data engineering or machine learning. And if you want more interpretable model, L1 might be a good choice. If you're looking for more like a machine learning solution or a stable model, then L2 might be a good choice. Or else you can think of combined L1 and L2 together. So next I'm going to show you some Python code demo for Ridge and Lasso. I'll show you how it is actually, how they are implemented. Okay, so let's look at the strategies, how we implement regularization. First, I'm going to show you Ridge. The code will be provided in the description below. And this is a Ridge regression. The first step is to find the optimal value of alpha. So let's take some dummy data here. And this is my data and corresponding response variable. And let's say that we have lambda. I'm going to take lambda 10,000 of them to find out which one is the right one. And I'll space it out between the interval log space, minus 10 and plus 10 to the power. And these will return 10,000 lambdas in between the range here. Let's take each of these lambda and train the ridge model with that particular alpha, fit and get the coefficients, save the coefficient in the array, and we're going to plot the coefficient. The next step is here, plotting the coefficient. Since there are 10 columns in our data set, if you see there are 10 columns here, so you get 10 coefficients. And if you closely look here, with this high value of alpha, all coefficients have become 0. That's not desirable. With a very low value here, low penalty term, that means you are staying with the same linear regression. This is also not desirable. This is also not desirable. Somewhere in between might be optimal. Now, which one is optimal? Which point is optimal? Let's do a quick grid search to find that out. So yeah, so this would be a grid search. Now, grid search is the grid search library. Take the same lambdas that we prepared earlier. The ridge model, run the grid search. Depending on the size of the data, typically this will take a lot of time. So I'm not going to execute it here. So all the lambdas and then the scoring parameter to judge which model or which value is the best one. You can also go for cross-validation, say 5 or 8 or 10. Run this, and then you ask for best lambda, and this is the value is returning the best lambda, which is very, very small. You can try a random grid search also to get a quick understanding as to what it is. But the random grid search means you have to try a few more times, like 4 or 5 times you get, so that you get to know what's the, approximately what's the right value of lambda. So this is the first step into coding the regularization, finding the optimal value of lambda. Next piece of code is actually implementing, let's say, the house price data and the ridge model. Implement the ridge model like a linear regression, no big deal. So that's your data set here. And this is my data, X and Y. Scale the data always for regression and divide it into training and testing. Linear regression just to see, what's the coefficient with the vanilla linear regression. And what is the R square? So this is the R square with the vanilla linear regression. Is the model overfitting? In this case, it is not overfitting because the training error and the testing error more or less the same. So you can't say that this is overfitting. This demo is not to show you the exact benefit of regularization, but rather outline of how to code the regularization like ridge. So visual, first check the value of alpha, like in the previous code. Find the right value of alpha, optimal value. Try the grid search, exactly the same process here. And once you find the alpha or the best alpha, then you can configure your ridge model with that alpha and then run the ridge model here. In this case, the improvement is really not much, maybe some decimal points. But if you closely take a look at the coefficients here, the coefficients after regularization, this is coefficient before regularization, or with a simple linear regression. Notice here the coefficient is very high. Here the coefficient has been reduced. Let's look at this one. This is pretty much the same here, but this one has been reduced. Okay, so you can see how optimization to coefficients is done by the ridge model. Pretty much the same happens with the lasso as well. I'm going to attach the code in the description. Take a look at the lasso. The first step is to find the right value of alpha, and then once you find it out, use the lasso model. ElasticNet is a combination of L1 and L2, and here there are two configuration parameters that you need to tune for. One is the L1 ratio, another one is alpha. Both alpha we have seen earlier. L1 ratio, exactly the same thing. Let's say your data set, and you can configure various alpha L1 ratio. For example, here I can have these L1 ratios and try grid search CV and find out the best L1 ratio for this particular data set. Then you can commission and build your elastic net after you have found the best L1 and best alpha. I hope this code is useful, and I'm going to attach the code in the description. So the next topic, before I go to the next topic, combined regularization is essentially elastic net, and I showed you how to go about coding the elastic net. The best practices with elastic net is hyperparameter with its L1 ratio and the alpha. Scaling is required, like in any regression problem, we should always scale it. Combine with other techniques, other feature selection techniques, not just depend on L1 or L2 or elastic net. And the next topic is going to be our, interesting topic on dimensionality reduction. Thank you all. We'll see you in the next session.